Good morning, folks. This is Todd Coburn of Cal Poly Pomona with Aero 3261, Lecture 22a on thin-walled pressure vessels. The analysis we're going to cover today has many practical applications in aerospace. The basic idea is that we have a structure that is closed and has a pressure acting on it, either a burst pressure, which is quite common, or a crush pressure. And because of that burst and crush pressure, there's going to be loads that develop in the structure that are tangent to the surface of the structure. And there are also going to be bending loads that develop. As the structure gets thinner and thinner, the loads that are not in the plane can become relatively negligible, and the dominant loading is in plane. These are called membrane stresses because they act as if the thing were a membrane. If you imagine a balloon has the wall of a balloon has like a near zero bending stiffness, but the balloon can carry a lot of pressure because it takes it all in a tangent direction in the plane of the surface. All the loads are carried in tension in both directions, and so that idealization of a thin-walled member with negligible bending stiffness and only axial stiffness is a common one in engineering. We use it for cables, that's called catenary action, and for plates, that's called membrane action. And there are many examples when we have lightweight structures like aircraft and rockets and satellites. There are many structures which can be idealized as a pressure vessel or a membrane structure. Once again, the stresses are going to be in plane, such that the stresses normal to the surface are zero, and therefore it's called a plane stress element. If we consider a cylinder to start with, subjected to pressure, we're going to find that that membrane stress develops, and we're going to get two directions of stress. If we cut a free body diagram by just slicing the thing in half and sum our forces, we can determine what kind of stresses we might see. So let's say we sum our forces looking at figure 741 of Behrend-Johnson's Mechanics of Materials. If we sum our forces in the z direction, we see since this is a hollow cylinder, we see the only area that was cut is that little thin wall of length dx and thickness t. The stress, if the stress on that in the z direction is sigma 1, then the force on those two little areas, top and bottom, is that stress times the little increment of area, where the increment of area is simply dxt. If we sum our forces in the z direction, we then can determine what that relationship between the pressure and the stress is. The sum of the forces must be equal to 0 if we're not accelerating. That means the stress times the area, we've got the thickness, top and bottom, so we got two of them, delta x. That's the forces acting in the positive z. And in the negative z, we have that pressure acting on the area of the circle, which is length dx and height 2r. So 2r dx times the pressure. So the question is, what r is appropriate for this? Well, that r would be to the inside surface of that cylinder. If you go beyond that, the pressure is only acting inside, therefore it would be that little r. Now if the pressure was external, to be strictly correct, you would take the r going out to the outer surface, which would be r plus t in that case. But we're talking about an internal pressure, and so we're going to just use r being to the inner surface. And we're going to also note that if the wall is thin, like super thin, the thinner that wall gets, the closer r inner is the same as r outer. So often these equations will be simplified. They'll just be identified as r, and you're wondering, is that the inner radius or the outer radius or the midplane radius? And we're just saying r is r because there's not a whole lot of difference if your r is large and your thickness is t. You got that? But for strictly correct equation, this would be, for this particular figure, internal pressure, that would be the inner radius. If we solve for this, we're going to find that the stress is just PR over T. This is called the hoop stress, and this is used throughout all the engineering disciplines. You could think of this as this stress is PR over T, or it's Purdy. So this is a Purdy stress. The hoop stress is a Purdy stress, and it's the stress that holds this thing together. And what we're saying is this pressure is causing this thing to get larger and larger. And as it gets larger, it's stretching in this direction. And as it's stretching, as it gets larger, it was this size, and the pressure makes it larger and larger and larger looking at the end of this thing. And so if we look at a little element on the surface, we see that the stress holding it together is this hoop stress, which we're calling sigma 1. We might call it sigma 1. We often call it sigma H for hoop. It's the hoop stress. It's Purdy, PR over T, where R is really the inner radius for an inner pressure. R is the outer radius for an external crush pressure, but we usually just call it R because if the wall is thin and R is large, then R outer is about equal to R inner, which is about equal to R at the midplane of the skin. So we're going to use this approximation even though it's not strictly correct. In our equation that we developed right here for this internal pressure is actually the inner radius, but we're going to find that we often just use R as R. Okay? So if you picture this cylinder and it's being held together, this hoop stress is the one that holds it together like this. So if you have the two halves, it's the part that's pulling like this to hold it together. That's your sigma hoop. That's your hoop stress. Okay, it's really important to understand that. So in this picture here, this sigma 1 is our sigma hoop, and it's a Purdy stress, PR over T. It's just the pressure, the radius over the thickness. You got that? Now if we cut another section axially, we're going to get another free body diagram. So let's just study this a moment. Once again, what we have is if we cut it in this direction, the only structure that's left is this area between the outer radius and the inner radius. That's the area that resists the stress. The area of that is going to be 2 pi r times the thickness, right? Now what r is that? That really is the midplane radius. So while this radius was Ri, this radius that we're going to use here is actually R midplane. Once again, we're going to pretend those are the same radius, and that's only true if R is large, is very large relative to our thickness. But we're going to make that gross assumption. So 2 pi r midplane times T is the area. The total force then would be whatever that stress is, we're going to call it sigma 2, times that area. That will give us the force holding it together, right? And what we're going to see if that pressure is internal, if we look at the end of this thing, so that internal pressure is not acting on this area here, it's acting on this area here. So what that is working against is we have that pressure times the area. What's that area? Well, it's pi r squared. What r are we talking about here? Once again, this is talking about Ri. So this equation uses Ri, and the pressure acts on Ri if we have an internal pressure. But it's reacted at the midplane. Once again, we're going to use that approximation that Ri is about equal to Ro, which is about equal to Rm. That's a key thing, because what we're going to do is write this equation, and we're going to pretend that R is R is R is R. And that is actually not correct, but it's close enough for government work, which ought to scare you a little bit. Got it? So if we sum our forces in the axial direction, we're going to see that 2 pi RT, once again that's the midplane radius, right, minus p pi r squared, that's the inner radius, is equal to 0. We're going to pretend that those two r's are roughly the same, and that allows us to develop this equation. This is the equation for the longitudinal stress. So we see these two stresses. We've got the hoop stress and we've got the longitudinal stress. The hoop stress acts to hold the two halves of the cylinder together. If you have a cylinder, the hoop stress acts to hold it together, and the longitudinal stress holds it to keep it from blowing the ends off. So because this has capped ends, it develops the longitudinal stress in this direction, and because of the internal pressure, it has this pressure trying to split it apart. If you imagine a big barrel full of liquid, you can see that the internal pressure is trying to rip it apart along this surface here. That's our hoop stress. And if we had the ends capped and filled it with pressure, then the force acting this way would tell them to blow it apart this way, and that's our longitudinal stress. If our hoop stress is per d, then our longitudinal stress is half as pretty. So the longitudinal stress is only half as attractive as the hoop stress. So what we have is the hoop stress is pretty and the longitudinal stress is 1/2 as pretty. You got that? Now if we have a sphere, we can do the same thing. We're going to get two stresses, but we make a section cut. You'll notice for a sphere, no matter how you cut it, you get a diagram similar to when we cut the cylinder in an axial for an axial cut, and we find then that both of the hoop and the longitudinal, they're both PR over 2T. So we see that the spherical, any kind of spherical membrane stress is also half as pretty as a hoop stress of a cylinder. You got that? And because our stress is in both directions, once again, if we remember, we got a little stress element. If we take a little stress element on the surface like this, there's our little element. If this stress is the same as this stress, remember we found from Moore's circle that this minus this over 2 is the shear stress. That means no matter how you rotate this element, no matter what orientation it has on the surface, there will always be these two principal stresses and 0 shear stresses anywhere. Now remember, that's in plane shear stress. If we actually look at the element, it has a little thickness, and even though this stress is sigma 1 and this stress is sigma 1, this stress over here is 0. That means if we take the difference between these two stresses over 2, we find out there is a max shear stress, and it's actually sigma 1 over 2. And because it's sigma 1 over 2, that means it's PR over 2T over 2, which is 1/4 PR over T. And our Moore circle then looks like this, which you should be becoming very familiar with drawing by now. This is another way of showing the same thing. Once again, for a cylinder, this is kind of summarizing. For a cylinder, we get the two equations, the hoop stress, which is pretty, and the longitudinal stress, which is half as pretty. And for spherical vessels, all the stresses in any direction are going to be half as pretty. Got it? For cylinders, we have a hoop stress, sigma 1, a longitudinal stress, sigma 2. Both of these are associated with 0 shear stress. Therefore, these points are plotted directly on Moore's circle. You can see sigma 1 at point A, sigma 2 at point B. And since this is a thin plane stress element, the stress out of plane is 0. Perpendicular to the skin, we have 0 stress. That means for a cylinder, our shear stress is going to be 1/2 of the difference between the stresses. For in-plane load and for out-of-plane load, we're going to get sigma 1 minus 0 over 2 is our max shear stress for a rotation of the element. Now if we have an aircraft, so a lot of aircraft we said are pressurized. What that means is when we go up to elevation, we're going to get pressure stresses. So if we have a fuselage like this, the inertia loads are going to be causing down bending, which is going to be causing a moment. It may also cause some axial load, and that means for any little element on the top, we're going to get normal loads, and we're also going to get pressure loads due to the pressure. So we're going to get normal loads due to our axial load and bending, and we're also going to get longitudinal loads. And in this direction, we're going to get hoop loads. And we may also have shear from other loadings like this. That would be for an element on the top. For an element on the bottom, it'll be similar. Once again, now the bending will probably be sigma axial plus bending, probably be compression. And we're going to get the hoop load still on the longitudinal load. There's our longitudinal component. And we're going to get our hoop component. And if there are other loadings, it'll be very common to also have shear on the element. Now remember, the hoop stresses and the longitudinal stresses, those pressure stresses, cause no shear stress in plane, at least not in the principal directions. But if we have inertia loads, which they could include axial and bending and shear loads, then that could end up causing that element to have shear on it, not because of the pressure load, but because of other loading like torsion and things like that. So what's our hoop stress for something like this? It's just per d, PR over T. What's our longitudinal stress? PR over 2T. Does this have any practical significance? Of course. This is how a lot of aerospace analysis is done. Does the pressure act on the inner mold line, the midplane, or the outer mold line? Well, if it's a burst pressure, it acts on the inner mold line, but we're going to ignore that and just call it R. Is the stress carried at the inner mold line, the midplane, or the outer mold line? Well, actually, both for the hoop and longitudinal component, it's carried at the midplane of the skin. But we're going to pretend that that R is just the same. Does that make sense? So, how do we apply this principle? Well, if we have a fuselage, we can analyze that fuselage for whatever bending load and shear. So if we take a little segment of fuselage, we're going to have a bending load, an axial load, and a shear on the thing. And that means any little stress element that we pull out of it will have axial load and shear. Because we have pressure, if we have internal pressure, we will also get a longitudinal component of stress and a hoop component of stress. So the total stress state will include the axial load and bending components and the pressure components. Generally, our inertial loads will just cause loading in plane. Let's look one more time, a little element of stress like this one right here. If we have axial load on the fuselage, that's going to cause a little component of axial load. It's probably going to be compression. This is our axial stress due to axial load. If we have bending stress on any given element, we will also get a bending stress. This will be either tension or compression. Up on the top, it will probably be tension, and on the bottom, it will probably be compression. If we have because we will have a transverse shear, and we're going to get a shear stress on the element, and if we have a torque, that will also induce a shear stress. Now if we look at our fuselage, we know axial load will give us a stress constant around it. Bending will give us a stress. It's going to be max tension up here and max compression down here with 0 here near the middle. Transverse shear will give us a stress that develop, and actually let's draw that. Let's see, our axial distribution will be like this, constant. Our bending distribution will be tension on the top, compression on the bottom. Our shear will give us a distribution of stress that increases. So we have max shear right here at the window belt where some idiot cut a hole in the fuselage, and minimum stress top and bottom. If we also have torsion on the thing, then our torsion will give us a constant shear stress acting all the way around the thing as it resists that torsion. So looking back at our stress element, we have our axial stress due to axial P over A, our bending stress MC over I. We have our shear stress, which is a combination of the VQ over IT stress and the TR over J stress due to the torsion. If we also have pressure, we're going to get a longitudinal component of stress, which is going to be tension for an internal pressure, and we're going to get a hoop component of stress, which is also tension. This stress, the hoop stress, is per D, and the longitudinal stress is half as per D, and those get superimposed on all the other stresses. So our total stress state looks something like this. While the hoop and longitudinal stress may have been plotted on Moore's circle like this, there's our sigma, our hoop stress, there's our longitudinal stress, that's our out of plane stress, giving us these little circles. The total stress state will actually have other stresses such that the total normal stress on this X face is going to be the axial, bending, and longitudinal component combined. The stress on the Y face will be just the hoop component. But both of these will see a shear stress that's a summation of the VQ over IT and the TR over J kind of stresses, which may mean that when we plot our Moore circle, if we're doing that, we will need to come out here to whatever that stress on this face is, plot it here, and if the shear stress is like this, it plots below the axis, we plot that stress and then end up striking whatever curve we have. As we've said before, Moore circle is a very handy tool. It's not used a huge amount anymore in industry, but is a useful tool for evaluating stresses. So that covers the stresses that develop on pressure vessels due to internal or external pressure. Be sure to watch the video on developing simple rocket loads and the one to understand how to evaluate strains, transformation of strains.